Next up, we have, let's see, Out of Sight from Scott. So BlindMate Network Backplane. So Scott, go ahead and turn it over to you and take it away.
Well, thanks everyone. So to talk a little bit about this project, I'm working with Submer, and one of the things that has been an interesting topic to us is the area of robotics in the data center. So when it comes to enabling robotics in the data center, how do we transition from something that very much has been hands-on to when you create a robot, do we really need to replicate the function of human hands when it comes to cabling connectors and such, or starting to explore some more BlindMate ways of doing things? So that has really been the initiative of the project is exactly that. So when it gets into the difference between hands-on and hands-off, it's I suppose from a perception perspective, hands-on and can be considered a good or a bad thing. Same with hands-off. So when I go through my experience, probably very much so I remember in my AboveNet days, early data centers during the .com boom, the cliche photo of spaghetti knotted cables that are throughout the data center and throughout the rack kind of give the epitome of understanding kind of hands-on cabling before scale was understood. Scale was creating kind of the spaghetti kind of side of things. And then cleaning up those cable bundling. I remember we did a lot of that in the Yahoo days. And then you get into a scenario where you have these big, beautiful cable bundles, and it kind of becomes that old adage of clean, fast, and kind of low cost, pick two. Then when it comes to serviceability in the rack and why we're kind of exploring this BlindMate connectivity is in the earlier days, I remember big stacks of Dell servers back in the Yahoo days, and we grew from 22,000 servers a year to crossing 100,000 in a single year. And I never thought anything would grow that big, but it did. And the whole idea of when it came to installing those servers, masses of human hands kind of blooding themselves as they catch themselves on the rack in the server. So, those are just a couple examples that kind of drove into this mission of, if we look at several initiatives around the idea of how do we become a kind of autonomous at the rack level, robotic serviceability, and then maybe at the same time having some additional benefits when it comes to kind of increasing the density that you can do with cabling and kind of improving the serviceability at the same time. So again, this is kind of what drove this, is the premise of, serviceability on the rack has always been hands-based, and kind of like what it says, hands are big, expensive, and hands are arguably the most common mistake in the world. So looking at making things hands-free, and I think in the open compute movement, a lot of that's already been accomplished kind of from the electrical side with the backplane of power in the back of DC power, and then also even as kind of the mission goes towards BlindMate connectivity, even in fluid connectors and such. So really, this is what kind of drove the intention of this project here, is really simplifying cabling complexity, densifying network connectivity, and kind of magnifying this path towards robotic serviceability. So this is kind of the first two missions, the first of two missions that we've kind of gotten into to do that. So looking at the rack level, what our mission here is kind of building upon, this is not the first time we saw this. Huawei and some others in the group had started to work on this, and we really wanted to build something functional and workable that had a design that we could kind of create quickly, test internally, and then really open source these designs as part of the movement, which is what we've done. So what we did initially is really what you see here is a backplane of connectors at the 1U level that enable room for kind of the power shelves level, consolidate onto a header, which I'll explain in a following slide, that could consolidate network connectivity. and begin and test this. So really what we have here is this mounts on the back of the rack. We've made some efforts to try to avoid, still accommodate the center DC plane in the middle, stay out of the way of kind of this emerging fluid planes that happen on the side, and also give some mobility in regards to movement, the way things can go as we continue to morph and get more people involved in this design. What you're looking in this backplane here is a 2N design. So basically a complete A and B path. Most people, including what I work on myself, wouldn't necessarily need full A and B cabling on the network side of things, but this is a demonstration of what that would look like. So this functionality, you kind of see the A plane on the left side, the B plane on the right. One of those planes could provide the full functionality of N, where both of them in this case kind of provide kind of A plus B functionality. Each one of the rack U ports feature a 12 differential pair. And in looking at that, you can see the specifications that we work for on the left, ranging from 10 gig Ethernet all the way up to PAN4 functionality at 110 plus gigabits per second. So having a broad specification in regards to what's possible to do over those pairs. Because I do work in kind of a high density fluid cooling environment, giving enough pairs per rack unit, and we did 12 in this particular design, which could be increased or decreased depending on the use case, we think gives a really good functionality for high bandwidth applications, particularly as compute gets denser and denser kind of on a per rack unit perspective. And we consolidate all of these into 216 differential pairs, which I'll get into when we explain the header. This is what the configuration looks like in a rack. And we also have some live photos in this. So as you can see, kind of A and B that I went through in the first slide, this is what the unit looks like in the back of the rack. And really what you can see is you can see the kind of 12 differential pair connectors that are at the individual rack unit. You can see where the power shelf plugs in. We have a single connector for that shelf. And then you can see the header connectors where we're consolidating all of this connectivity at the rack switch layer, which I'll get into when I get into that. The rear views that you can see there on the left, you can see kind of a 1U server that's not fully plugged into the DC bus as well as the header. This would represent a 1U switch. Where on the right, you can kind of see those nodes, both the 1U switch on the top and the 1U server node at the bottom, both unplugged on the left and plugged in on the right in regards to what it looks like. The cable that we're using in this particular specification. Now we are working, we very specifically went with a twin axial cable initially with the intention of following on with fiber optic connectivity as well. So this twin axial cable, which we're working with Samtech with on cables and connectors as a first step, is also compatible with our dielectric fluid cooling that I kind of do in my full-time job. So getting this to work in both the standard OCP rack as well as some more, I'll call it next generation dielectric fluid environments and such. So this twin axial cable, as well as the connectors, were one of the first things that we qualified, as well as I think at the rack level will be more frequently used. So this was the twin axial cable is really the first specification we went with, and now we're following up with fiber optics, which now we've also qualified in our fluid. So, probably the big challenge on this is meeting the functionality of up to PAN4 connectivity is quite common in this type of cable, at least nowadays. So this is a traditional, 2 center conductors. It's got kind of one outer dielectric structure conductor. On the cable side, everything from the conductor to the contacts that you're going to see on the connector are all direct soldered. Across kind of every layer in the connector, there's a one-piece ground structure to kind of decrease crosstalk. From a distance perspective, this is a passive cable because it's designed to be in the rack. So really what you have is kind of 7 meter to 10 meter maximum distance limitation, which we see working really well at the rack level. And probably one of the initial concerns in developing this is the bend radius. So as you can imagine, these cables from these connectors that I'll go through at the rack unit on the next slide to these headers, when we're consolidating, 216 pairs in this channel, that's, several inches deep. The bend radius and the density of that channel to be able to accommodate up to this level of connectivity was key. So bend radius became pretty important. So looking at the rack unit, these are the increments. So again, we kind of initially partnered, and Samtech has been really generous in kind of contributing to this project in regards to their connectors and their expertise and such. And so what you can see here is you can see kind of in the lower left side of the pictures, this is kind of how the connectors in their guides mount onto the channel in the back of the rack. And then you can see kind of the connectivity, how it plugs into the node and such. And you can see what else is important in here. Durability specs. So again, when you have a rack that can have continuous kind of upgrading of server infrastructure, swapping of servers and such, you've got a durability spec of basically, plugging in and removing 2,500 cycles, which I think across the life cycle of hardware, even of the most problematic hardware at, a longer 5-year plus operational cycle should fully accommodate. Your environmental specs are incredibly broad for all kinds of different kinds of environment. Your blind mating force specifications, which as we've gotten into robotics and such, becomes less challenging on this level. It's about 6 pounds of blind mate pressure to really form and firm this connector and its guides. Where on the header, which I'll get to next, you kind of have a bigger potential challenge to pay attention to. So the consolidation header. So really the intention here is to, when we were looking at this project, we could have done a number of things in regards to where does the backplane of these 1U swappable servers go. We could have very much gone to a patch panel, which would have been, one approach that we've actually done. The second approach is there's real potential benefits of again, when you look at transceivers and even twin axial or fiber cables that are connected through transceivers, a lot of that is designed again for the human hand. And what you can see here is across these 4 connectors, which, total, 128 millimeters wide, you get 216 lanes or differential pairs of connectivity, which is enabling a heck of a lot more density into what could be kind of a next generation rack switch that's also completely swappable by robotics and such from an automated perspective. So what we decided to do here is to consolidate this connectivity, these 216 lanes, into a single rack unit to represent how kind of a newer form of hands-off connectivity on a rack switch can enable much higher density of connectivity to connect into that switch. Now, what you can see on these connectors is because this is a heck of a lot greater number of contacts and conductors, you have a blind mating max force for this complete assembly of about 60 pounds. So for those that have worked in blade chassis and such, when you handle hardware by hand, you're traditionally are going to use points of leverage to be able to plug that in. When we've worked with early robotics functionality, the robot actually doesn't need those form of leverage, which is again, is kind of a difference of human hands versus robotic hands. But as you get this density, you see kind of blind mate force pressure going up. So again, like going back to the header, and really what we're seeing is proposing the idea, whether it's within fiber optics, which we could have fiber pairs at also incredibly high density in less space once you get human hands out of the picture. as well as in the twin axial pairs here, is the whole premise of could just simply removing all the space restraints of our current form of connectivity and densifying that connectivity, could this enable a 1U switch to handle this form of density without, a lot of the silicon photonics designs that we're looking at now are starting to go more and more towards a path potentially of not having external transceivers, which again takes a lot of that space. And when you look at this, this is in one rack unit, 216 differential pairs times 2, because it's A and B, as you can see in the picture. And that form of density, if we were using transceivers and hand form connectors, would be nowhere near as possible in that form of density. So again, kind of just being provocative in thought here in regards to, can this form of connectivity enable the density of rack switching to get that much better, while at the same time enabling robotic serviceability of this particular gear. So that's the premise of what we've done. The easier approach in this particular case could have just as easily been, we're going to create a patch panel to be able to create a patching kind of scenario where manual patching could occur between the switch and the patch panel, which is more commonly the case. But again, I think it defeats the premise of having this kind of blind mate connectivity across the entire rack level. I think having the switch on that is could be equally as important. So that's what we've experimented and tested here. This is what it looks like for real. So this is the backplane. And again, you can kind of see the space for the power functionality. You can see the 48 volt DC bus in the middle. You can see where the rack switch would be a 1U rack space. And then you can see in the standard kind of server node space where the server nodes would plug in. Again, underlying that you don't necessarily need A plus B complete functionality in many cases. These are some close-up views. As you can gather, the guide in regards to just ensuring that the connectivity, we've added additional guides at the header level, as well as at the 1U level, to ensure that connectors can't get damaged and everything aligns properly. So in both of those cases, you can see on the cluster of 4 header connectors, as well as even the individual rack unit connectors, instead of just using the single guide that is part of the connector, we actually added these additional guides to ensure that integrity. Obviously, this is a mission critical part of the rack. So to kind of wrap things up on this, this is the team that has kind of started this. So from a submirror perspective, we've worked on backplane and header design, and I would say it's not really our intention to get into manufacturing this kind of solutions. Our interest level in getting involved in this is, again, particularly with this COVID scenario and everything going on, is what are the important things that need to be kind of open in the industry, open standards to be able to enable robotic serviceability of things. And I would argue that there's 2 things, and this is really the first of 2 things that we hope to be helpful and contribute. And that is A, blind mate connectivity on the backside, and then B, what does the interface between the robot and hardware look like from a standard perspective? Because I think that it can't be done up team different ways or many different ways in order for robotics to be able to work with all hardware and such throughout the data center. So that was really our intention in getting involved from a submirror perspective. Samtech, we talked to several partners, and Samtech, like I said, was incredibly generous with their engineering resources and offering connectors and cables to be able to develop and test this solution. So their engagement and their interest in OCP and contributing is also very valuable. Where at the same time, I think the reference design that we're going to be releasing to the community to now improve upon as a group offers the functionality for other connectors as well. So again, we didn't want to lock into any kind of single source. And then 2CRSI, which is works closely with us in Europe in regards to server integration was actually when it came to building test nodes that had those, switch functionality at the 1U level with the mock-up header connectors, as well as the A and B connectors on the server side, were a really good help. So along those lines of things, anyone interested in this project, like I said, we intend to hand off all of our work to the community, and we want to continue to be involved in it, but getting more involvement and kind of taking some of these really early steps and turning them and continuing to polish them and make them better is really our intention here. So Raul from Submeris, who's kind of the project lead on the project. So any kind of interest in this kind of scenario, any kind of feedback and everything, we're really looking to try to be helpful in advancing this from these initial first steps that we've kind of done. So from a time frame perspective, just to give an idea, we started to dive into this. This has kind of been our COVID time work, and we've driven this work across 2 continents, and we've gotten to a point where we've begun kind of our alpha testing, validating functionality, and now bringing this to the OCP community today. So again, I think that what's important relative to call to action is if anyone is interested in this and feels that they can offer feedback or really would like to contribute expertise that can make, like I said, I think a good foundational base much better is really our intention. We'd love for anyone to join in, making sure that this type of connectivity and complements and doesn't get in the way. We've been talking a lot in the conference about version 3 of the rack, and there's all kinds of scenarios in regards to fluid manifolds and will a single DC bus accommodate increased high power densities in the future, and just ensuring everything kind of interoperates at the back of the rack in a smooth perspective. And I would argue that the more and more that we have things like fluid manifolds and perhaps 3 DC buses that went to 1 that maybe could go to more in the future for density, I don't know, but again, densifying and keeping hands off of that back of the rack just to be more efficient from a space and a productivity perspective could be helpful. And converging these efforts into top of rack switch, like I said, I was looking at connectivity of, is there the blind mate rack switch as well as the blind weight nodes, I think are really cool. So again, we're going to be sharing all of our information and really look to that contribution to continue. So what you see here is just to get a little bit of view. So what you have here is an OCP rack. You can see the mock-up server that 2CRSI has helped us out with many. That actually this is an example of a node where you're going to be able to see the blind mate connectivity, and then you're going to be able to see some of these early robotics perspectives. So like I said, when you start paying attention to what is the interface between a robotic hand and the server look like, that's a really important thing, and we intend to offer some of our early efforts in that to the open source community as well. So our goal really is to come back next and kind of begin to offer some of the first robotic related reference design to the OCP community as we discuss this as well. Let me see if I can get this video to play and we can just take a quick look at how this blind mate connectivity is working. So, that kind of gives an idea. And I just wanted, we've got a lot more to share on this. And this is, again, more like COVID time work. And I think what I wanted to show here is really underlining the concern that we have at the front of the rack. How is a robotic fingers or hand going to interface with a rack? Does it make sense to design the robot to operate as nimbly as our hands or as fat-fingered as our hands? I would argue it isn't. So what does robotic handling at the server and nodes look like? And then on the back side of things, would we really create a fat-fingered, nimble robotic hand? Perhaps it would be a little bit too expensive versus some of the intention of this blind mate network connectivity overall. So robotics efforts that we've been working on and such are some of the things that that's motivated us to this project. And doing so in an open source perspective is really key. So that's what we've been up to. That's what we intend to share, and hopefully that is helpful. And even more hopefully, we hope to get some smarter people engaged so we can make this better and better. And thank you.
Cool. Thanks for that, Scott. We are right at the end of time here. I know there were a couple of questions that did come in. I think what we'll probably have to do is maybe Gabby, if you could maybe post those. You've already posted them in the chat. Maybe we can just answer them through the chat, because we do unfortunately need to move on to the next presentation here. So Scott, on the FN Virtual Tool, if you could go on there and maybe look at a couple of those questions that were posted, I'd appreciate that.
Absolutely, and I'll stay on for a bit. If anyone wants to engage a little bit, be happy to do so. But thank you.
Thanks, Scott. Richard, I see you're in the room, and welcome. Looks like